Hi everyone. In this video we will conclude our discussion of section 6.6, which is about a model for hyperbolic geometry. So before we go further in section 6.6, it's probably a good idea for us to review where we have been in hyperbolic geometry up to this point. Remember that hyperbolic geometry is based on the SMSG neutral axioms, that is, axioms 1 through 15, together with the hyperbolic parallel postulate. So remember, the hyperbolic parallel postulate says that if you're given a line, some line and some point external to the line, then there are at least two lines passing through that external point that are parallel to the original line. Now we can build a giant theory for hyperbolic geometry, just as we have done in the past for Euclidean geometry. But one thing we would like to know before we go proving a whole bunch of theorems is whether this hyperbolic geometry has a chance of being consistent. Now remember from chapter 1 that we can show that an axiomatic system is consistent if we can produce a concrete model for it. And so that's sort of the point of section 6.6. We're going to build a model for hyperbolic geometry. Now, it won't be exactly a concrete model, but it will be a model that lives within the Euclidean plane. And so what this will mean is that, that hyperbolic geometry will be at least as consistent as Euclidean geometry is. So, well, what do we need to do to make a model? Well, there are two things. We first have to have an interpretation of the undefined terms and relations, and then we need to show that that interpretation satisfies all of the axioms that we want it to satisfy. So here our interpretation of hyperbolic geometry is the set of all points interior to the unit circle. So in the picture here, the red circle is the unit circle. All of our points are going to be Euclidean points inside the unit circle. And then our lines in this interpretation are going to be of two types. They're going to be either diameters of the unit circle, as shown here, this diameter through the center A of the circle, or they're going to be portions of circles that are interior to the unit circle and are orthogonal to the unit circle. So that's a line of this type. Now remember that these points at the ends of the lines, those points actually aren't on the lines because remember that we're only considering points that are interior to the unit circle. Okay, so with that interpretation, we have begun already to verify that each of these axioms holds. Now, we're not going to do, of course, all of the axioms. It's a great deal of work to do that. But we have already shown in class that axiom 1 holds. We've shown with a proper interpretation of distance that axiom 2 holds. And we have also shown that axiom 3 holds, which essentially says that the points on each line can be put in one-to-one correspondence with the real numbers in a way that respects the notion of distance that we developed in for axiom 2. We also learned how to, what angles look like in hyperbolic land and how to measure them. And in that discussion, we pretty much saw that axiom 11 holds. That is that to each angle, we can associate a number between 0 and 180 degrees. Okay, so today, what I'd like to do is two things. So first, I'd like us to verify that this interpretation satisfies the hyperbolic parallel postulate. And then after that, I would like us to make some explicit computations involving distances between points. So let's have a look at the hyperbolic parallel postulate. which, as we just mentioned, says that given a line L and a point P not on L, there are at least two lines through P which are parallel to L. So we want to show that this property holds for our interpretation. And here on the slide, you see this proof, which, you can pause the video and look at that if you want, but I think maybe the best thing for us to do is to look at a picture. So here's the promised picture that is going to help us illustrate the hyperbolic parallel postulate. First, I'll draw your attention to the green circle. The green circle is the unit circle. All of our hyperbolic points and lines are going to live in the interior of the green circle. So we start with this hyperbolic line L, which is shown in pink in the picture, and we choose a hyperbolic point P, which is external to L. And what we want to do is to create two hyperbolic lines that pass through P that are parallel to L. So the first line we can create by choosing point Q, where L meets the unit circle, our point P, which is off of L, and then we compute the image of P under inversion with respect to the unit circle, getting P prime. So if we take those 3 points, Q, P, and P prime, they determine a unique circle, which we will label M. So it's this orange thing. And if you restrict M to just points that are strictly interior to the green circle, you get a hyperbolic line passing through P. Now you can do the same thing with points P, P prime, and R. So if I take those 3 points, I can produce a blue circle, N. And if I look at the points that are on N that are interior to the unit circle, I get a hyperbolic line, again, that passes through P. So notice that both circles M and N are orthogonal to the unit circle because both circles contain P and P prime, right? So there was a theorem back in chapter 5 that says that if you have a circle containing P and P prime, then it must be orthogonal to the circle of inversion. And so that means that, the hyperbolic lines in orange and in blue are really legit hyperbolic lines. Okay, so really the only thing left to do, now that we've got these hyperbolic lines passing through P, is to check that they are both parallel to the pink line L. Now, if you look at the figure, you might object and say, look, they're not parallel to L because they hit L at points Q and R. But remember that our hyperbolic points are points that are strictly interior to the green circle. And so while the circles M and N do meet the pink circle at Q and R, those points are actually not points in the hyperbolic disk. And so those are not points of intersection of the corresponding hyperbolic lines. So now what's to stop us from having some other point of intersection between, say, hyperbolic line M and hyperbolic line L? Well, let's suppose that we did have a point of intersection. So let's suppose that we had a point A that is, say, in the intersection of those two hyperbolic lines, M and L. Then, because the circles M and L are invariant under inversion, we know that A prime is in both of those circles. And we know that Q is also in both of those circles. So then what we have is we have 3 points, A prime, and Q, that both lie on circle M and both lie on circle L. But we know that 3 distinct points determines a circle uniquely. And so that means that M and L must be the same line, or excuse me, the same circle, right? But that's a contradiction because, remember, P here is a point on circle M, but it is not a point on circle L. So that means that these two hyperbolic lines determined by circles M and L cannot intersect. Now, if you do the same argument, you can show that the hyperbolic lines determined by N and L do not meet either. So therefore the hyperbolic parallel postulate does hold in this model. So it can be kind of fun to use compass and straight edge or GeoGebra to produce figures like the one that we saw on the last slide. So in this example, what we're going to do is we're going to start with a hyperbolic line. In this case, it's going to be just this diameter of the unit circle. And the external hyperbolic point is going to be this point P, which has coordinates 0, 1/2. Now, to produce 2 hyperbolic lines that pass through P and are parallel to our given line, which I'll call L, we need to produce 2 circles that are passing through P and are orthogonal to the unit circle. So remember from the last slide, we can get one of those circles, by looking at P, this terminal point Q, and P prime, which is the image of P under inversion with respect to the unit circle. So those 3 points, Q, P, and P prime, go together to form this circle centered at point E. So all 3 of those points are on that circle centered at point E. Now to get the other circle, we look at our points R, P, and P prime. So we can use those 3 points to form another circle centered here at H. And then what I do is I just draw those circles using GeoGebra, and I look at the portions of those circles that sit within the unit circle. And those are my hyperbolic lines passing through point P that are parallel to line L. Now we're going to step back and consider some of the difficulties involved in computing the hyperbolic distance between 2 given points. In this example, we're going to be computing the hyperbolic distance between A, whose coordinates are -0.2 and 0, and B, whose coordinates are 0, 0.8. Now, you might remember from the hyperbolic distance formula that to make the computation, I'm going to need to know the coordinates of the points P and Q, where the circle that determines the hyperbolic line joining A and B meets the unit circle. It's not immediately obvious what those points P and Q are. to figure out what P and Q are, we need to know something about the common circle that contains P, B, A, and Q. We can learn something about that circle by computing the images of both A and B under inversion. So the image of A under inversion is, A prime, it's out here somewhere. Okay, and then the image of B is B prime, which is up there somewhere. And then I can use both of those, the segments, A to A prime and B to B prime, are going to be chords in this circle that contains P, B, A, and Q. So, if I look at perpendicular bisectors of those segments, I can go and find the center of my circle, which is going to be this E. And I realize here that A prime has been placed sort of in the wrong place. It should be further, much further to the left. But at any rate, we have now found the center of our circle. And once you have the center, which is about minus 2.6 comma 1.025, then you can produce the the equation of this circle. So now to find points P and Q, it's a matter of finding the points of intersection between this circle and the unit circle, which is x squared plus y squared equals 1. So those will give us our points P and Q. Now, that could be something of a mess algebraically. But luckily, Desmos comes to the rescue. If we go into a tool like Desmos and we plot both of these circles, then we can ask it to compute the points of intersection, P and Q, and it will come back and tell us these coordinates for P and for Q. And then once we have that information, we're ready to compute the hyperbolic distance between our points A and B. So remember, it's a formula involving the logarithm, natural logarithm, and we take the Euclidean distance from A to Q divided by the Euclidean distance from B to Q, multiplied by the Euclidean distance from B to P divided by the Euclidean distance from A to P. So you make that product, then compute the natural log, and then the absolute value. And when you do that, you wind up with this number 2.4676. So that number, that is the distance in hyperbolic land between point A and point B. Oh, and one more thing. The magic words are green beans. So happy Thanksgiving, everybody.